First, we create a new Three.JS scene. This scene is essentially a container that holds all of our 3D objects, lights, and cameras. Next, we set up the camera that will capture the scene from a certain perspective. Here, we're using a perspective camera with a field of view of 75 degrees, an aspect ratio based on the window size, and viewable distance range from 0.1 units to 1000 units. We need a renderer which will create the final image that we see on the screen. Here we're creating a WebGLRenderer, setting its size to fill the window, and adding it to the document so it's displayed in the browser. Now we set up the Canon.js physics world. This is a separate environment where we define physical properties such as gravity, which we're setting to mimic Earth's gravity, pulling objects down at 9.82 meters per second squared. In Canon.js, we need to define shapes that will act as the foundation of our physics bodies. Here, we create a sphere shape with a specified radius that we'll use for our ball object. With our sphere shape ready, we can now create a physics body by defining its mass and attaching our sphere shape to it. This body will have physical properties like velocity and force. We position our sphere body at the coordinates 0, 10, 0. This places the sphere above the ground, allowing it to fall under the influence of gravity when the simulation starts. We position the camera along the z-axis so we have a clear view of the action. Here, our camera is moved back 5 units along the z-axis. Switching back to Three.JS, we create the geometry for our sphere using the same radius as the Canon.js body, ensuring they match visually in our scene. We create a material to define the appearance of the sphere. This basic material is set to a yellow color. We combine the geometry and material we've created into a Three.JS mesh, which is a drawable 3D object. The newly created mesh is added to the Three.JS scene, and the Canon.js body is added to the physics world. These are separate processes, since one relates to visual representation and the other to physical simulation. We define an update physics function to synchronize the Three.JS and Canon.js worlds. Inside, we advance the physics simulation by one step, which is typically 1/60th of a second to match the frame rate, and then we copy the position and rotation from the physics body to the mesh. To create a ground surface, we start by defining a plane geometry in Three.JS with a width and height of 10 units. We also need a material for the plane. This one is a basic gray material that is visible from both sides. Similar to the sphere, we create a mesh for the ground by combining the geometry and material. To lay the plane flat like a ground, we rotate it around the x-axis by -90 degrees or pi over 2 radians. In Canon.js, we create a plane shape for the ground. This will represent an infinite plane that bodies can collide with. We create a physics body for the ground, and by giving it a mass of 0, we make it static, meaning it won't move no matter what happens in the simulation. Finally, we define the animate function, which is our animation loop. Request animation frame is called with animate to create an infinite loop, calling update physics to keep the physics world and the graphic representation in sync, and renderer render to draw the scene from the perspective of the camera.